Alright, so my construction for finding my origami construction for finding a very accurate approximation to pi on 4 is closely related to an infinite series that I discovered, which I don't actually know how to finish it because the denominators get so goddamn huge. But, so what's happening is to get a finer version of this, the second term, instead of just being 1 minus square root of 2 on 2, that quantity, times 4/15, you divide it by the square root of 14. And that'll get you about a little bit better than 15 times more accurate, which means that you can take your unit from being 4¼ inches to being about 5 foot 4 inches, and your error is still on the order of about 0.8 thou. So your error is still within the width of a sheet of paper. It's still the same size as it would be, right? But then the next term of this sequence, so they all have, you can think of it as they all have the unit function of square root of 2 as the numerator, unit function of square root of 2 being 1 minus square root of 2 on 2. And then what happens is for the first term, you're dividing by the fractional component of square root of 2, so you just get back the fractional component of 1 on square root of 2, which is 0.7, which is square root of 2 on 2. Then, yeah. Then the second term is unit function of square root of 2 on square root of 14. Then the third term is unit function of square root of 2 on the square root of, what is this, 560,017,593, which is, if you look at it after term 2, the difference between pi on 4 and what we've generated at that point at term 2, the difference is if you process it right, it would have a denominator of just smaller than the square root of this. Right? If you take it and square it, it gives you something like 560,017,592 point something. So yeah, it's the next integer up, and the same thing with the 14. And then the same thing with the next term. The denominator for the next term is the square root of that number, that big number, 182193025338817569130523269. At that point, there's as many digits as you can represent in on a calculator. There's as many digits in that number as you can represent digits on my calculator anyway. Yeah. So at that level of precision, 4 terms, it's maxing out my calculator. My calculator cannot tell the difference between what this is giving me and pi on 4. It cannot tell the difference. Yeah. So you're going from 0.414 to whatever the hell, the fractional part of the square root of 2, to square root of 14, to the square root of 560 million, but to the square root of fucking whatever the hell that is. And then the next term would be even more astronomical. So, like, it gets more and more accurate as you go out. And the craziest thing is, as far as I've seen it, the component that is here the component that would be perfect for there, when you square it, it's almost always exactly an integer. It's right under an integer. It's like here it was like 13.9955 or some shit. For this one it was like 592.99 something. This one, the next digit was 68.9. The calculator couldn't show me any further than that. So like they're almost integers anyway, so that's why this is getting you such ridiculous precision. I don't know if there's a rule yet that can generate these numbers so that we could just have all of them. That would be really nice. But even at this level, I don't know if it's helpful, because like memorizing this is just as hard as memorizing these levels of this number of digits anyway. But it is kind of interesting that just in 4 terms is like boom, it just exploded to being that precise. And it's utilizing, it's directly employing things that I had to invent in order to handle other things. So that's interesting.